We have been talking about various fundamental theories of axial flow turbines. So, by now you are aware that axial flow turbines in modern aircraft engines, typically in gas turbine engines in aircraft usage, and of course, those which are used in land based gas turbines, which are indeed much larger. The all turbines that are used, axial turbines that are used, are essentially multi-stage turbines. That means, there are more than one stage lined up one after another, just like multi-stage compressors, to supply sufficient amount of aggregate power to the compressors. Now, in case of land based gas turbines, the entire power that is generated by the multi-stage turbine is used in compressors or for taking out power for grid power generation, electrical power generation. In case of aircraft engine, the multi-staging is done for a number of purposes. It still has to supply power to the compressor. It can also supply power to the propeller, as it used to do in the early days of gas turbine plus propeller, that is turboprops, many of which of course, are indeed still around. And then of course, it supplies power to the fan or the big fan, as most of the present aero engines are, which are turbofans. So, turbines actually supply power to all of them, the propellers, the fans, the compressors, and in the process of this supply of power, it is necessary that certain amount of aggregate power is indeed created by the turbine, and when that aggregate power creation requirement is more than a certain amount, you have to go for multi-staging. Now, in terms of our understanding, we may say that there are certain criterion related to the gas turbine parameters that we have been talking about, the pressure ratios of compressors and turbines that we have been talking about. And with reference to those parameters, we can say that certain numbers, once they are exceeded, we would need to go for multi-staging. Today, we will also be looking at multi-spooling. Now, multi-staging and multi-spooling are two different things. You can have a multi-stage turbine, which is a single spool turbine. On the other hand, you can have multi-spool turbine, which have to be necessarily multi-stage, but multi-spool, as we have seen in case of axial compressors, they are two different groups of compressors running on two shafts at different rotational speeds or RPMs. Now, that requires a different mechanical arrangement to be introduced into the overall engine configuration. So, that obviously requires far more people to agree to the business of multi-spooling. So, we will be talking a little about multi-spooling also in today's class as part of multi-staging, and we shall also talk a little about how this multi-spool arrangement of turbines needs to be fundamentally matched to the multi-spool or multi-stage compressors. When you have multi-spooling, each spool independently needs to be matched to the corresponding compressor, and we will have a quick look at the fundamental relations or fundamental considerations that go into that matching between compressor and turbine to effect finally multi-spool arrangement. So, these are the things that we will be doing in today's class, that is multi-staging and multi-spooling. There are a number of criterion or considerations based on which multi-staging and multi-spooling is normally adopted for modern axial flow turbines, which are normally part of overall gas turbine engine. Let us look at some of these fundamental considerations that go into adoption or selection of multi-stage configuration for axial flow turbines. So, the considerations that normally go into multi-staging and multi-spooling, to begin with, let us look at the multi-staging requirements. Normally, it comes from the aggregate amount of shaft work that needs to be produced. Now, as I mentioned, this shaft work includes the work that needs to be supplied to compressor, that work that needs to be supplied to fan, and or work that needs to be supplied to a propeller. In case of a land based gas turbine engine, the shaft that needs to be supplied to compressor and work that needs to be supplied to the external power generation unit would have to be supplied from the turbine. Now, so the overall work that needs to be done by the turbine needs to be assessed and computed, and on the basis of that the multi-staging arrangement needs to be decided upon. Now, to begin with, if the turbine pressure ratio requirement is more than 2.5 and in a modern one a little more than 3, typically multi-staging would be resorted to, because a single stage turbine can give you pressure ratio or pressure drop of the order of 2.5, and you can probably stretch it to 3, but anything more than that typically you would need to, in a commercial engine, you would need to resort to multi-staging. On the other hand, the compression ratio over the years of gas turbine engines have kept on increasing, and as a result, to supply that much of aggregate power to run a multi-stage compressor, multi-staging of turbine has also become inevitable, especially in the aero engines and more so in the land based gas turbine engines, which are anyway much bigger than the aero engines, and they are getting bigger and bigger and bigger, and in them multi-staging is almost an inevitable result of the present configurations. Now, the number of stages of course would have to be a round number, an integer, and that has to be decided by the state of art of the turbine design, in the sense the first stage is in the aero engines typically likely to be cool turbine. So, it may take more pressure ratio or work done. In the following stages they may not be cooled, in which case they may do lesser pressure ratio or pressure drop and the work done. So, the split between the stages would have to be decided, and integer numbers of stages would have to be decided upon, so that you have 1 or 2 or 3 stages in which the total amount of work is accomplished. So, this is how multi-staging is typically resorted to. Now, let us take a look at why and how multi-spooling is done. Now, multi-spooling is necessary if the compressors have split in more than one spool. Most of the modern engines actually are 2 spool engines, 2 shaft engines. There are of course quite a few which are already 3 shaft or 3 spool engines. Now, the spooling is something which is decided by the engine designer or engine configuration, and as we have done before and as we may have mentioned before in case of compressors, that the 2 spools run at 2 completely different RPMs. For example, one of the spools may be running at 7,000 RPM, another spool may be running at 10,000 RPM. If it is a military engine, the one of the spools may be running at 10,000 RPM, the other one may be running at 16,000 RPM. So, this is something which is decided by the engine designer, and then a certain amount of matching between the turbine and the compressor is necessary spool wise to decide upon the split of work, the split of pressure ratio, and of course, the speed or the RPM at which each of these individual spool should be running. So, that is something which is decided in a much larger manner, bringing into reckoning the design and the features of the compressor, or for that matter if it is going out to an external generator. So, those things would have to be decided taking into account units other than the turbines as well. Now, if you have a turboprop engine, which is a gas turbine plus a propeller to power an aircraft, multi-spooling is often necessary or resorted to, so that the propeller has a set of turbines or at least a turbine to supply power to the propeller through normally a gearbox. So, when the particular shaft is hooked to a gearbox, its speed would have to be controlled through the gearbox to supply a lower RPM to the propeller. Now, this is an arrangement which is typically necessary for turboprop engines, and this allows the other spool, that means the turbine compressor combination, to run at a different RPM, normally at a higher RPM, and as a result, as we have seen before, you can have a spool of turbine, compressor and combustion chamber, which is often called the core of the engine. So, that allows the spools to run at different speeds, and it allows a core engine to be configured or decided upon, which is a combination of compressor, turbine and combustion chamber. So, some of these are decided upon not only by the turbine designer, but by the engine designer, and taking into account many factors that come into the engine design. Now, most of the modern aero engines are indeed actually at least 2 spool. There are actually very few 1 spool engine these days. Very small engines can be 1 spool, but moment it acquires a certain size, most designers would like to go for 2 spool. It has a number of inherent advantages. One of the things that we have talked about while talking about compressors is that if you run one of the spools at a lower spool, notably the first set of compressors, that is the low pressure compressor at a lower RPM, and then allow the second set of compressor, that is the HP or high pressure spool, to run at a higher speed, then the high pressure compressor can supply compression in a steady manner and deliver it to the combustion chamber. Now, that spool of compressor would have to be run by the high pressure turbine, which takes the gas straight from the combustion chamber and then runs it at a high speed. So, the combination is that the inner turbine and the inner compressor of a gas turbine engine run at high speeds and at a steady high speed, whereas the outer spool, that is of the compressor and of the turbine, that is the front set of compressors and the rear set of turbines, run at a lower speeds. Now, front set of turbines do actually have to face, as we have discussed, some of the non-uniformities and some of the changes of the atmosphere from which the air is coming into the compressor. Similarly, the rear set of turbines or the LP turbines would have to face the varying changes of the gas state as it is going through the nozzle and to the atmosphere. So, rear set of turbines are also kind of subject to certain change of state from the rear of the engine. So, from the front of the engine and from the rear of the engine, certain changes of state of the air or gas is probably inevitable, and as a result of which these stages, if they are run at a somewhat lower speeds and then brought to the control through a control mechanism or control algorithm to steadier or safer speed operating conditions, then you have a better control over the engine operations to ensure that at no stage either the compressor or the turbine gets into any kind of operational problems. So, those are the issues based on which normally spooling is done. So, spooling is typically something which is also related to engine controls, and something which you may have done in other courses, and those controls would invariably then come into play in control of the spools, which are controlled independently, which need to be controlled independently. So, that is about spooling and multi-spooling of the engines and multi-spooling of turbines, as we are talking in today's lecture. Let us take a look at some of the standard engines. What we see here now is a single spool engine with a multi-stage turbine. So, we have one spool on which the compressors and the turbines are mounted. Now, as you can see here, the compressor consists of a two-stage axial compressor, then a centrifugal compressor, a single stage, which delivers to combustion chamber, which delivers to the turbine, and this is a two-stage turbine configuration, but both are mounted on a single shaft or spool. So, as a result of which this is a first step towards multi-staging of turbine, but it is still on a single spool, which is running both set of compressors here. One set is actually axial compressor, another is actually a centrifugal compressor, and this is a kind of configuration which is very popular typically with turboshaft engines, which are used in helicopters, and they run of course at very high rotational speeds or RPMs of the order of 25, 30, 40,000 RPMs. So, this is a kind of configuration that is used in certain kind of engines, and as I mentioned, notably in the turboshaft engines, which does have a multi-stage arrangement of turbines, but they could possibly be on the single shaft. On the other hand, if you look at this configuration, in which you have two multi-stage turbines, two stages, one is a single stage HP, another is a single stage LP. So, you have a two stage configuration, but they are on two different spools. So, one is on one rotor over here, and that is on a one spool, and second one is another rotor over here, which is on a different spool. So, this is a multi-stage, in fact, indeed a two stage, but a two spool turbine layout. This is used, this particular picture is from a military engine, which actually which means that one spool of, that is one stage or HP stage, actually supplies power to the HP compressor set, which may be a multi-stage compressor, and then the LP turbine, which is again a single stage turbine, supplies power, the entire power, to a LP stage of compressors of this particular engine. So, and as is shown here, just as a aside, this engine has a little bit of a bypass. So, this is the bleed air or the bypass air that is going past the turbine and not getting into the turbine. So, we can have a two stage turbine, which is a two spool turbine, and we just saw a two stage turbine, which is a single spool turbine. So, those are the possibilities that engine configuration and engine designer would have to be involved with the decision making, whether it should be multi-stage, multi-spool, or whichever way the decision needs to be taken. And this is a very large aero engine, which actually is a 3-spool civil aircraft engine, and what is shown here is a very large number of turbines. This is of course your combustion chamber, where the gas is created, the fuel is burned, and then this supplies into, of course, the HP turbine, as we know, the high pressure turbine, which produces very large pressure rises, and then it goes into another set, which in this particular configuration would be called, or is normally called, intermediate pressure turbines or IP turbines. That is a set of about 3 stages, and then finally, it goes through the low pressure turbines or LP turbines. So, it has 3 spools, and this is one shaft, this is the second shaft, and this is the third shaft. So, it is a 3 shaft or 3 spool civil aircraft engine, normally a very large civil aircraft engine used for large aircraft. So, there are quite a few of them, they are not in majority as yet. One of the problems of course, with 3 spool is that you need to have control over all the 3 spools. So, you need mechanical and good control system to effect control over all the 3 spools in a desired manner. So, 3 spool is actually a very futuristic concept, and it is probable in future we might see more and more engines that are 3 spool engines. Now, if we are looking at multistaging, one of the first problems that multistaging would throw up is how to create the flow track of this multistage configuration. We have just seen that you have all kinds of flow track starting from here, from the delivery of the combustion chamber, and this flow track has to be designed. Okay. Now, we will be talking in a separate lecture on how the blades are designed. Okay. So, design of turbine blades would be taken up in a separate lecture, but today we will just have a quick look at how this flow track is indeed decided upon or designed, because as you can see, this flow track can be something which has a strong bearing on the aerodynamics of the flow through the turbines. So, the simplest way of looking at it is a part of a cone, which has a subtended angle of twice gamma, and then this is decided by the change of height of the rotors and stators. Rotors are called stators are also called nozzles. So, you have nozzle rotor. So, it is a multi-stage arrangement, and this is presumably a HP turbine, and this is a LP turbine set, and in between there is a little bit of a gap where there is nothing, no blades. So, we have a multi-stage simple configuration in which the middle or the mid height remains constant radius. So, it is a constant mean radius flow track design, which is again the simplest, and that is what people used to do in the early days of gas turbine design, is the simplest thing to actually get into in your design. Now, what it says is that if you take it as a simple part of a cone, then all you have to decide is what the cone angle should be, okay? And this cone angle can be deduced from the various sizes and the shapes of the turbines. So, we have the shape size of the actual length of the entire turbine multi-stage arrangement, and as you can see here, that is going to come into picture in deciding what this conical angle should be. And then of course, the number of stages would have to be decided, as we have done in the previous lectures. The number of stages would have to be decided by certain aerothermodynamic considerations. And once you have decided number of stages, then you have to decide the split of the number of stages into HP and LP, and then take some kind of a decision on what should be the gap between HP and LP. And then of course, you have the actual length of each turbine row of blades. So, you have nozzle axial length, rotor axial length of each stage. So, all of it put together, and then of course, you need to decide what should be the gap between the rows of blades, that is delta S. So, all of it put together gives you the total S, or the length of the entire turbine, and H 1 is the first height, let us say annulus height, okay, of the entry stage, and H 2 is the exit height of the entire multi-stage configuration. So, when you put all of them together, you get a certain tan alpha, which can be deduced from this relationship. Somewhere in between, we have used a ZP, which comes out of the Z, which is number of blades, number of stages, and it gives some value of ZP, which is 2 Z minus 1. So, when you put this simple geometric or trigonometric relationship, you get a conical angle tan gamma, which is a straightforward conical shape to encase or accommodate this multi-stage configuration. So, that is the simplest way of configuring the flow track of a multi-stage turbine. Now, the other thing that does happen is flow through the blades is non-axial, and it it goes something like this. It goes through the rotor like this. As we have done before, there is a change of area from A to B. There is acceleration here, then it goes out, enters the rotor, and again there is a change of area from C to D. So, this is nozzle, this is rotor, and in a multi-stage you have another nozzle, then you have another rotor. So, more number of stages you have, more you have nozzles and rotors, nozzles and rotor, and in each of them the flow goes through this kind of turning. So, the gas flow coming from the combustion chamber executes this turn, huge turn, as we have done in the earlier lectures, then takes another fairly large turn to the rotors, does the work or gives up a lot of energy to the rotating shaft, gets into the next row of nozzles, again takes a huge turn and a large acceleration, then gets into the next rotor, now takes a huge turn, gives up again a lot of energy and makes the rotor rotate. So, that is how the flow proceeds through the individual rows of blades, which are nozzle, rotor, and more the number of stages you have, more the number of nozzles and rotors you have, and the flow would proceed along this manner through each of these rows of blades. Now, you have to remember that this happening is varying from root to tip. So, the amount of turning it does in each row of blade, whether nozzle or rotor, would be actually varying from root to the tip of that particular blade. So, the fundamental aerodynamic parameter actually is variable from root to the tip of each single row of blades. So, if you look at the earlier diagram, each of these rows of blades has varying kind of turning, and that turning is varying from root to the tip of each blade. Okay. So, this is happening inside a turbine, and hence the turbine designer needs to have very good idea about what is happening in terms of aerodynamics or simple gas dynamics, and he has to invoke all the aerodynamic and gas dynamic theories to analyze the flow and finalize his design. The actual flow track in a modern multi-stage also goes through not the kind of simple cone that we looked at. It often goes through this kind of a curved or curvilinear passage. We of course, know from simple continuity condition that the flow has to have expanding flow track or a diverging flow track. That diverging flow track is likely to be a curved diverging flow track. So, you have stator, rotor, stator, rotor, stator, rotor, etc. It may finally have exiting stator or it may not have. It depends on the turbine designer. Many turbine designers normally may not like to have another stator over here, another exit guide vane if he can. Sometimes the engine design may force him to have a exit guide vane over here, as is shown here in S4. And then of course, it goes into the passage, which finally in case of aero engine would go into the nozzle that creates thrust. So, this curvilinear passage of flow first through the blades like this, it comes in, goes like this and then goes like this. It is a lot of curvature it executes at a particular radial station if you take a cut, and then if you look at sideways, it goes through a passage like this. Okay. So, the flow is executing a very complex curvilinear passage through the turbine blades before it is exiting the turbine and going either into exhaust or into the nozzle. So, this needs to be analyzed in great detail before you have some idea about the aerodynamics and the complexity of aerodynamics of the turbine, which you require to create turbines of reasonably competitive aerodynamic efficiency. So, the multi-stage flow analysis needs to be done. So, you need to do a flow track design, which comes from, as I mentioned, a continuous application of continuity condition, which will keep giving you the values of the heights or the annulus areas at each of those stations. So, you can calculate the values of pressures and temperatures of each of those stations after a nozzle, after rotor, after nozzle, after rotor, etcetera, etcetera. And then that will allow you to calculate the density. You also need to take a call on the actual velocity, and then if you do that, you apply the continuity condition, and then each of these stations you have your annulus area, which then, knowing what the mid or median radius is or median diameter is, you can then calculate the annulus height. So, that is how you get the height of the blades from simple continuity condition application. So, first thing is you need to create the flow track by indeed applying the continuity condition, in which you have to take a call, you have to take a decision about what should be your actual velocity at each of those stages, and then of course, that will allow you to create a smooth flow track. You need to have a smooth flow track. You can't have a flow track that is exact. We have seen that in case of compressors also. Now, the flow tracks are modern compressors are generally curved the way I showed in the last slide, and the flow through the blades is curvilinear through the blades. So, this requires application of 3D flow analysis techniques. So, flow is indeed naturally through the turbines highly 3-dimensional in nature. So, you need to apply 3-dimensional flow analysis techniques to analyze the flow and then finalize your design of the turbines. So, the modern turbines are analyzed indeed through 3D flow analysis techniques, and then you need to apply 3D CFD techniques, analytical techniques that are available, or whatever is made available to you. Simple 2-dimensional analysis would fall short of the requirements of modern turbine design. So, 3D analytical techniques would need to be adopted very rigorously for modern turbine design. So, this is a look at the modern multi-stage, multi-spool turbine, in which you have a HP, which itself is a multi-stage affair, and then you have a LP, which again is another multi-stage affair. So, and in between, as you can see, there is a large interspool duct or gap, which is created, during which, as you can see, the flow actually has moved from a median radius, which was here, a lower radius, it has moved to a higher median radius, and it has continuously moved to a higher mid radius, which of course tells you very quickly that this designer wanted to continuously upgrade his value of u or u mean of each turbine. As you know, the rotating speed gives you the blade speed, and that blade speed, if you can upgrade it to higher values. So, the blade speed here could be much higher than the blade speed here, and this whole spool is running at the same speed. So, the average blade speed here is substantially here. In fact, as you can see in this particular picture, the mean here is well above the tip here. Okay. So, the u mean here is substantially higher, and that was indeed the intention of this particular designer. On the other hand, in HP, where the mean radius here is much lower, substantially lower than even the first stage over here. However, the HP turbines normally run at much higher RPM, as we have discussed before, and as a result, it is entirely possible that the blade speed of HP turbines is at least of the same order as the blade speed of LP turbine, the last LP turbine, okay, if not actually a little higher. So, as I mentioned, the two spools run at substantially or significantly different rotating speeds, in which case the mean speed of the last turbine and the mean speed of the first turbine may actually be almost of the same order, even though they are at a different radial setting. So, that is how the engine designer configures the entire multi-stage and multi-spool turbine. One of the things which I mentioned is you need to do compressor turbine matching, and so this is just a very quick block diagram matching. If you have a single spool, you have to match this compressor with this turbine. If you have two spool engine, you have to match this compressor with this turbine, and then the HP compressor with HP turbine. So, this is your HP spool, this is your LP spool, okay, and this is your intermediate, that is station 1, 2 between LP and HP, and 3, 4 is the intermediate station between HP and LP turbine. So, this is the how the spooling is normally to be done in an overall gas turbine environment. Now, if you have a 2 spool high bypass turbofan, what happens is one spool, that is the HP compressor and the HP turbine spool, would remain as we saw in the last one, whereas the LP turbine spool would end up running a set of LP compressors and a very large fan, which is part of the turbofan configuration, which produces, as you know, cold thrust. So, the LP turbine has a lot of jobs to do, and as a result of which it would actually be supplying a large amount of aggregate shaft power to the combination of this fan and compressor. One can probably make a guess that this is what this particular turbine is doing. This large turbine is it has 1, 2, 3, 4 stages of turbines. They are essentially supplying power to a combination of compressor and a large fan in a turbofan configuration. Now, the single spool power that is produced by the turbine has to be matched with that of the compressor. Now, this is the work matching between, this is the left hand side is the compressor work, right hand side is the turbine work, and this is what actually gives you the finally the matched compressor turbine configuration. Whereas, if you have a 2 spool configuration, the matching has to be done spool wise. So, HP turbine compressor has to match with the HP turbine work. KHP is a parameter that has been created, essentially a thermodynamic parameter, to stand for this pressure ratio. We saw that in the earlier one also, which is nothing but a parameter that takes care of the temperature ratio across the turbine. So, basically it is a work matching between the turbine and the compressor, which gives rise to the HP balanced matched turbine compressor configuration. Then you have to do the same thing separately for LP. So, you have to match the work done by the compressor and the turbine, and you get again another matching parameter KLP, as you got earlier in case of KHP. So, this gives you, this is called often a matching parameter, and this finally gives you the matched values of compressor and turbine work done. From this matching, you can actually then figure out what are the matched values of compressor and turbine pressure ratios at that matched design point. So, that matched point is indeed the design point, and at that design point, you from here you can find out what is the matched compression ratio and what is the matched turbine expansion ratio, for which the compressor LP HP and then turbine HP LP would have to be designed separately by the compressor designers and by the turbine designers. So, this is how the configuration is finally arrived at before the blade design is indeed taken up. So, this matching is an essential part of compressor turbine design, and this has to be done before you actually embark on compressor or turbine design. Just to take a look at the fact that if you have a multi-stage turbine, you have to match those two spools. So, we were talking about compressor turbine matching, you have to match the two spools. So, you have to match HP turbine with LP turbine. Now, this graph gives you an idea what happens when you have a matched HP and LP turbine. This is post facto, that means after they have been designed and their characteristic maps have been created. So, this is your HP turbine characteristic, this solid line, and then this is the exit of the characteristic. This we normally give it by the entry characteristic, but you can draw an exit characteristic. So, let us say this is your design operating point, which you can now extend to this exit characteristic point of the HP turbine, and then from there you can proceed from here onto the LP turbine, and this is your LP turbine characteristic on the basis of its entry conditions, and you get this characteristic point on the LP turbine, which now as you can see is a good operating point, because this flat zone over here and indeed this flat zone over there, as you have discussed in the earlier lectures, actually correspond to choked flow condition, that is a steady turbine operating condition. And then of course, you can extend that to the exit condition of the turbine, LP turbine, which you may like to extend later on to matching with the nozzle if it is an aero engine. Okay. Or if there is another stage after this, supposing this is IP turbine, you have to match that with the LP turbine. So, you can extend this to whatever the component is following, okay, and then try to do the matching on this characteristic map. So, this is how the two spools of the turbines need to be matched before you have set upon the detailed design of the turbine. This is just a quick look at what could be a possible 3-spool high bypass turbofan engine. As you can see here, we have 3 spools. This is the innermost spool of HP compressor and HP turbine. In between, of course, you have the combustion chamber, and then you have the intermediate spool of intermediate turbine, which runs the intermediate compressors. So, the compressors here are separated from the turbine from the big fan, and the big fan is independently run by another set of turbines, LP turbines, which are the outermost turbines. So, outermost turbines run the outermost compressor or the big fan, and the intermediate ones run themselves, and the innermost compressor and turbine run each other. So, this is how the 3-spool configuration is typically made, and we saw a 3-spool engine a little earlier, a picture of which indeed is based on this kind of spooling. So, we can say that the compressor turbine spool by spool matching needs to be done very meticulously, and this needs to be augmented in actual operation by various engine control systems. So, more spools you have, more complicated control systems you would need to create. So, this is, and of course, mechanically you are making the system more and more complex. So, this is something which the engine designers would have to decide. So, there are some companies who are comfortable going to 3-spool. They are comfortable with the mechanical complexity and the control system complexity, whereas some others are more comfortable with the 2-spool configuration and are finding various 2-spool variants to cater to large engine requirements. So, it is up to the particular company to decide what they are comfortable with in terms of the state of art of technology. So, you need to do all the things matching of compressor turbine, matching between the spools before you have a whole multi-spool, multi-stage arrangement of the entire engine. So, this is how multi-staging and multi-spooling is indeed done. In the next class, we will be talking then about 3D flow theories for turbine blade. As we know, as we have just seen, you have to have good 3D flow theories. So, we will be talking about the 3D flow theories in the next lecture in relation to axial flow turbines.